Hi, Logic students. I thought that I would make a recording for section 6.3. This is the section where we learn how to make truth tables for complete propositions to determine whether they are tautologous, that is always true, self-contradictory, that is always false, or contingent, that is sometimes true, sometimes false. And I thought I would demonstrate one exercise in section 6.3, part 1. Here's number 7. This is a statement that says if z then x and x or z, then x. And the task here is to set up a complete truth table for this statement and then to analyze the truth table to tell, again, whether it's a tautologous, self-contradictory, or contingent statement. Let me see if I can get the pen here, maybe a thicker one, so it's easier to see. The first thing we want to do is determine how many rows this truth table will have. So you see here that I set it up so that there are 4 rows, but how do I know that there are 4 rows? Well, there's a simple calculation that you can make. You count the types of letters that are in the statement. So this is a statement that has 5 tokens. So this is a token, this is a token, 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 and token. So there are 5, but the types are only 2. There's a type Z with 2 tokens, and there's a type X with 3 tokens. So there's 1 here, 2, and then 3. So there are 2 types of letters here. And there's a simple formula. So you take this as the exponent, and you put this as the base. You put the number 2 as the base. So the formula to figure out how many rows a truth table has is 2, because there are 2 truth values, true and false, elevated to the number of statement letter types that are in the statement. So because there are 2 types, Z and X, the calculation is 2 to the second, or 2 times 2, which is 4. So you know that you have 4 rows. And how do you set them up so that you capture all the combinations? Well, you start on the left with the first letter, Z. And since you know that you're going to have 4 rows, you split the 4. So you do 2 T's and 2 F's under the Z. And you need to be consistent. So if you put 2 T's and 2 F's under Z, then you have to do it under the other token of Z in exactly the same way. 2 T's and 2 F's. For the X, you take this column, 2 T's and 2 F's, and you split it again. So now it's 1 T and 1 F, 1 T and 1 F. And you do it again for all the other X's. 1 T, 1 F, 1 T, 1 F, and again for this one, 1 T, 1 F, 1 T, and 1 F. So now you have captured all the combinations. Okay, I hope this is clear. You count the types of letters that you have. You write down the number 2. Then, because you have 2 types, you put another 2 up here. And then you do the calculation. 2 to the second is 4. So you know that there are 4 rows. And then for the first letter on the left, you split the 4, 2 T's and 2 F's. For the other letter, you split again, 1 T, 1 F, 1 T, 1 F all the way. Then what you do is you start computing from the inside out. So first you look inside the parentheses, and then you gradually work your way to the main connective, which is this one. I think you can see that the whole statement is a conditional, where the antecedent is what is contained in the brackets and the consequent is the X. You can't put anything under this horseshoe just yet. You first have to see what's going on inside the parentheses and inside the brackets. You start with the contents of this set of parentheses, if z then x. And you know from the truth table for the conditional that when the antecedent is true and the consequent is true, the conditional is true. Then when the antecedent is true and the consequent is false, the conditional is false. When the antecedent is false and the consequent is true, the conditional is true. And when they're both false, the conditional is true again. This is something that we learned in section 6.2 with the truth tables for the basic logical operators. Now we use the truth table for the wedge because that's the main connective, the main logical operator in here. When they're both true, it's true. When one is false and the other true, it's still true. When one is true and the other false, it's still true. And when they're both false, it's false. Okay? So now we've figured out these two columns. There's a column under the horseshoe, and sorry, get rid of that. And I wanted to draw an arrow there. So there's a column under the horseshoe, and there is a column under the wedge. So we're going to use those to compute what goes under the dot, because this conjunction, the truth or falsehood of this conjunction, is a function of the truth or falsehood of the two columns, one under the horseshoe and one under the wedge. So this is a conjunction. You use the truth table for conjunction, and you know that a conjunction is true when the first part is true and the second part is true as well. So we put a T here. And the conjunction is false when one of the two components is false. So let's try to see if I can maybe highlight those two columns. It'd be easier to see. So if I can use a highlighter. So the columns that you want to pay attention to are this one and this one. Okay, so that may make it easier to keep track. I need to go back to the pen. So you have true and true makes true, and then if one of the two components of a conjunction is false, doesn't matter which one, the whole conjunction is false. So, but here again it's true and true. So the whole conjunction is true. And then here this part is true, the other part is false. So the whole conjunction is false. This looks a little messy, but it should be clear what is going on. Now everything else that you've done becomes irrelevant because the only thing that counts is this column, the one that goes under the main connective of the antecedent. Because you have to figure out what to put under this horseshoe. And the column under the horseshoe is a function of what is under the dot and what is under the consequent of the whole conditional, which is x. So you compare this column with this one. And you use the truth table for the conditional. True antecedent, true consequent, true conditional. False antecedent, false consequent, true conditional. True antecedent, true consequent, it's a true conditional. And false and false, true. Okay, so now the only thing that is relevant is this column here. This is what you wanted to produce in the end. And this shows you that the statement that we're working on is tautologous. It's a statement that is always true. Okay, so I hope this is useful, and I'll make another video for the exercises in section 6.2, which are slightly different. Let me know if you have any questions.